Well, hello, and welcome to the third video in a set of 3 videos associated with making some engineering calculations associated with propane, our propane tank, and just some intro to combustion of propane. So let's get started. So all of these images here on the title page, as you can see, are associated with burning propane to achieve some objective. And so what have we covered so far? Well, in the first video, demonstrated that it's really pretty easy to determine, based on our system here, our small propane tank, to determine the mass in there, the volume of the tank, and therefore the specific volume. Then got a little more fancy, jumped into chapter 3 to show you a technique for when we know we have a mixture of liquid and vapor within the tank. It becomes a pretty easy matter to determine the pressure inside the tank and pinpoint the state of the saturated mixture underneath the vapor dome. And in this module, just going to give you a little introduction into what you're going to have in chapter 13, which will be the last chapter you cover in the whole class. It'll be probably I think the last week of class. So let's kind of look at what we have. Oh, so I've got to go live. All right, so here's our system. Right now we have a closed system, don't we? But as soon as I open the valve on this propane tank, we're going to have an open system. So we'll do a little demo there. Before I light this thing off, let's because I don't want to move it around while it's burning. I'm going to get a little closer here. So what I want to do is look at the little holes here. Notice here, so this is made out of brass. Notice, I hope that you can see in these, there's 4 holes. There's 4 holes going around in here. Well, those are holes where the propane, which comes out of a small little orifice in the middle of this brass tube, a tiny little orifice, that's where the propane comes out at pretty high pressure. We found out what that pressure was, about 8 atmospheres, about a little over 800 kPa pressure. And so the propane flow will then entrain air to come through these 4 little holes. And so this part of the nozzle, you can think of that sort of as a little combustion chamber where the propane and the air are mixing together. We'll light it off with a spark, and then we'll have a nice stable flame coming out of sort of the end of this combustion chamber. Okay, so now let me go ahead and light it off. Carefully, I'll light it off carefully. And there it is. Now, and I'm not even at full throttle here. So I've just got, for right now, I've just got this valve. And so with the valve, so do you see that I can adjust? I can adjust the mass flow of the propane down to just like a little flame, but it certainly is certainly a flame, isn't it? Now, an engineer designed this nozzle and little chamber so that depending on the mass flow, the correct proportion of air is entrained into these little side holes. Okay, and so this is just like a little flame, but we'll go to full. We'll increase the throttle here. Wow, okay, a little more propane flow. And now we're at full throttle. So this is pretty much full throttle flow. And I can, so it's hot. So that the temperature, the flame temperature is hot. I can feel it on my face. And so since it's winter, it feels kind of good. It's heating me up pretty good, but certainly, obviously I'm not going to pass my hand through the flame to demonstrate we can do that. but it's pretty hot. And so you see, you have a nice stable flame that's initiated within that little combustion chamber, and then the combustion is completing itself even as it exits that combustion chamber. And so there's the blue flame. Okay, I'm going to turn my fuel off. And we'll look at doing some basic, sort of the startup of doing some combustion basics for the early part of chapter 13. Okay, let's start at the easiest part first. I think going all the way back to high school. So it is my hope that you got good at doing this in high school, or at a minimum in freshman chemistry, by looking at the combustion process for any hydrocarbon fuel, C sub M, H sub N, where now for propane, we've got C2H8. And in freshman chemistry or high school, you said the oxidant, what's enabling the combustion, is pure oxygen. And so your job in high school or freshman chemistry was to figure out these two numbers. What are these two numbers? And also, what are the exhaust constituents? What are the products of combustion? And so you did some talking back in high school or freshman chemistry, saying, well, for a hydrocarbon fuel that you're burning, the reasonable and actual exhaust products are carbon dioxide and H2O vapor. H2O vapor is just sort of an interesting product of combustion of any hydrocarbon fuel. And so your job was to figure out what's the numerical question mark here and what's the numerical question mark there. And that'll complete your burning of a hydrocarbon fuel with pure oxygen. Okay, and so the question is, whoops, there we go. I missed a slide. The first step is figure out these two question marks on the right-hand side. Let's see if I don't need a formula to do this. I can look, I've got to balance the atoms, right? Or molecules. So I've got to balance the carbon. So I've got two C's over here. So this question mark must be 2. Okay. And I've got to balance my hydrogens. And so I've got 8 single hydrogens over here. And so I'm going to need 4 diatomic hydrogens here. So this is going to be the number 2, and this will be 4. There we go, 2 and 4. And so once you've got 2 and 4, then you come back to figure out, well, how many O2s do I need to balance my equation? Well, I need 2 O2s plus, well, that's a single O, so I need 2 more of them, right? 4 single O's is going to be 2 O2s. And so let's see, that's going to be 2 plus 2. That's going to be 4, isn't it? Yes. Thank goodness I got that right. So there is our chemical reaction equation for burning propane with pure oxygen. Now, you say, well, that's real nice and that's really pretty easy. But what makes this reaction equation different than what we observed here in the real world just a minute ago? Well, we know that what's different is we're not burning what's going into these holes. The oxidant is more than pure oxygen, isn't it? It's air around the surroundings. And then I believe earlier in your class, so just in a week or so, it's my bet that your instructor is going to cover some of the details about what's our air made out of. Well, our air is made out of a number of gases, but the way we engineers model our atmospheric dry air is going to be a mixture of oxygen and nitrogen and a little bit of other ideal gases, but primarily for our engineering purposes, it's going to be oxygen and nitrogen. Okay, so the next level of sophistication is burning propane with air. And that's what we really did in our demo problem. And your instructor is going to explain, or you might remember, or you're going to be able to get out of your text that for atmospheric air, for every oxygen molecule, there are 3.76 moles of nitrogen molecules. For 1 mole or kilomole of oxygen, 3.76 kilomoles of nitrogen. That's the real world mix of oxygen and nitrogen in our surroundings. Okay, so that's air. So it's not too difficult as long as you just sort of, you can either commit that to memory, or that might be something that you would put on your formula sheet. If you can't remember 3.76 in your head, you'd want to note that somewhere, because we use that model in so many parts of modeling atmospheric air. Okay, so we've got to figure out this reaction equation. And so my claim is that, wow, if you study your same hydrocarbon fuel, you're going to get the same result over here on the right-hand side with your CO2 and your H2O. So really that 2 and 4, that comes pretty quick from previous work. We still got to figure out what we fill in for the numerical number for nitrogen that's in the products. And also we got to figure this out, this question mark out here too. All right. Now, let's see. That becomes pretty easy. Okay, this number here becomes pretty easy because it's the exact same balance. You've got to have your O's balance. So that number is going to be 4, just like before. However, you recognize you got something left over. 4 times 3.76 moles of nitrogen. So that's what this question mark is going to be. Okay, and there we go. That completes it. 4 times 3.76 is what that number. We don't need to go through do the calculator. It's just going to be 4 times 3.76, and you're done. And so that example right here, burning propane with air, I hope you remember in your head, what do you call this reaction equation? We call this the stoichiometric equation for burning propane with air. The stoichiometric equation, in other words, it's the exact amount of oxidant that you need to exactly combine with your 1 mole of fuel to get complete combustion, but it's the exact amount. Okay, so now in the real, how about this nitrogen? You say, okay, that makes sense. What's the difference between this equation and burning with pure oxygen? Well, I won't light it off again, but you see, it becomes apparent that the nitrogen really comes in and leaves, and it doesn't have anything to do with the combustion process. It's just sort of along for the ride. The nitrogen in the atmospheric air is along for the ride. And so what's the functional, your common sense tells you functionally, what effect will that have on the combustion? And the answer is that by having nitrogen coming along for the ride, that serves to decrease the temperature of the combustion. It decreases the temperature of the combustion products because it's along for the ride. It also has to be heated up from ambient conditions up to combustion temperature conditions. And so the nitrogen tends to decrease the flame temperature of combustion. So it's not so bad. Chapter 13 is not so bad. Okay. One more level of sophistication in our combustion reaction equation is very typically the individual, the engineer who designed this nozzle and little combustion chamber, they came up with their design trying to make us entrain a little more air than we really need for the stoichiometric equation. So in the real world, we're normally always trying to burn with a little excess air in order to ensure complete combustion. So in the real world, in my little example here in the video, I'm going to say, well, let's say this is designed to run about 10% excess air. That's just sort of a rule of thumb, pull a number out of the sky for an example, 10% excess air. How would we develop our reaction equation there? Well, what we'll do is we will set up kind of like the stoichiometric equation, except 10% excess air is going to be the same as 110% theoretical air, or in other words, 110% of the stoichiometric air. And so that's how I put this 1.1 times. And so these question marks are going to be exactly the same as the almost exactly the same as the stoichiometric equation. But notice here, since you're starting out with more than the exact amount of oxygens than you must have, there's going to be a little extra O2 coming out of the exhaust products. And so this last term here is going to be one additional element of the exhaust products, the little excess oxygen that you're not going to use for combustion. So we'll go down the path here, okay? And so let's see. So the first thing we do is we fill in exactly the same numbers as we had for our two exhaust products, CO2 and H2O, 2 and 4. We come back here and say, okay, well, that must be 4. And now I'm going to do the math going left to right. 1.1 times 4 times 3.6 nitrogens. Oh, let's go to the next step. There it is. So over here, we've got to figure out how many nitrogens we have in the exhaust products. Well, it's 1.1 times 4 times 3.76. So it's the same drill as before with the stoichiometric. And then with the oxygens, we have to figure out, well, we used up 1.0 of the oxygens for the combustion. And so what's left over is 0.1 times 4 times the oxygen. So it's going to be 0.4 moles of O2 left in the combustion products. And so a typical design of what we have here for our propane tip burning is, let's say, around 10% of excess air. And that's called a lean situation. So lean means you have more air than stoichiometric, more air than theoretical. And so it's common practice to have flames and combustion in the lean zone instead of a situation that is fuel rich, or in other words, more fuel than you have to burn, and you're just passing some fuel off into the exhaust gas, which is wasteful, monetarily wasteful, isn't it? So anyway, that gives you an idea for that. All right, now, so that gives you sort of an intro to chapter 13. Beyond balancing your reaction equation, then you're going to use thermodynamics to determine at what temperature will the propane burn with the air, and also how many, at what rate will heat be released as a result of the combustion, how much heat is generated from that chemical reaction, that exothermal chemical reaction. That's a good place to leave it here. So point I'm trying to make here in this one last, the third video in the set, is to demonstrate to you that the fundamentals build on one another from chapter 1 all the way to the end of chapter 13. Each chapter builds on another. And then the other point that I'm trying to make is putting in upfront work early in your semester is going to pay off for you throughout the whole course. It will keep you from panicking, and it will enhance your performance. So putting in some hard work up front, it'll still be hard work the whole way through, but it enables you to keep moving along instead of getting stuck and panicked and getting in an emergency problem situation. Okay, I hope that helps, and I hope all three of the videos help you with a fuller understanding of how your thermodynamics class fits in with our everyday world around us, and then the types of things that you might be experiencing once you move into that practicing engineer situation where maybe things aren't, all the given information is not provided to you and then you're expected to solve a problem where there is a known answer. So like I say, I hope that helps, and good luck as you continue your progress in this class.